everybody. Okay, got it. Just click got it. Yeah, so thanks so much for the invitation to come along. I'll just find the right screen to share, and then we should hopefully be good to go. Does that work?
Yes, that's working.
Perfect. Well, that's great. Okay, yeah. So I'm Dan Parsons. Thank you for the introduction. And I'm going to talk to you about a host of work that a range of teams I've worked with over the past number of years have pulled together, and the projects have a common theme to them of trying to understand how flow processes and sedimentary deposits are linked. So how the flow processes and the boundary conditions that shape them can ultimately control the stratigraphy that's produced within these fascinating submarine channel systems that exist on the bottom of many of our contemporary oceans, but of course have built up lots of the strata that lay around us, that we wander around and clamber over on land now. And of course, understanding those flow processes and understanding that process to product set of relationships is fundamental in terms of then being able to reconstruct paleo flows and then understand the paleo environments of deposition. So I should start by saying I'm going to be presenting work here that's been produced by a whole range of teams that I've worked with, including, and some of the slides indeed and the figures have been taken from others that I've been working with, and papers that we've produced together. Starting with Jeff Pekel at Leeds in particular, Jim Best out in Illinois. More recently, of the past 5 to 10 years, Pete Talling, who's now at Durham, Mike Clare down at Knox, Katie Meyer, who's across now in New Zealand as well. So sorry, I knew I'd get disturbed. Daddy's on the call, Munchkin. Okay, go and get it. Good boy. And then Katie Mayer in New Zealand, and Charlie Paul and the team at the Monterey Bay Research Institute. So all of those people and all of the teams that sit behind it have kind of contributed to the work I'll talk about today. The picture here, incidentally, on the background is a picture of the Congo Canyon, offshore of West Africa. And I'll be talking a bit about an ongoing project there, very exciting project that we have going on at the moment, understanding the flows and the deposits down this huge canyon system in the Atlantic. So let's see if this works. So move on. Of course, these channels across our seafloors and the Pacific have only recently been discovered, really, the past 40, 50 years, where technology, acoustic technologies, survey technologies have allowed us to begin to capture the sizes and shapes of these channels that extend across our sea floors. This one here is the Indus channel, where you can see lots of bends, lots of channel systems going across this big sedimentary fan deposit. And Rick Hiscott and Ken Pickering and others were involved in publishing some of the results from this survey that just gave us the glimpse of these features on the seafloor. And of course, they exist all up through different parts and different channel basins. They transport sediments into the deep sea. But there are others where they don't. So the channels that currently move just water associated without much sediment. But there are lots and lots of these channels. This is the Nemok channel up towards on the east side of New Zealand, where lots of recent work actually has been looking at how then sediments have moved down through this channel as a result of large tectonic events as well. So lots of these sorts of channels and systems are moving in and around these systems. Sorry, I got that mixed up. That's the Haringey Channel off of New Zealand. The Nemo is obviously the one up in the North Atlantic. And again, looking again off the coast of Labrador. This is one of the biggest, longest channels in the world, coming off the Hudson Strait, and then moving again across the abyssal plain. If you look at the lengths and sizes of some of these systems, we're talking thousands of kilometers long. So the longest river, terrestrial river, is the Nile at around 6,500 kilometers. But these channels can extend over similar distances, 3, 4, 5,000 kilometers as well. So they're of a similar scale in terms of their length. But if we think about channels across, I'll come back to this slide in a minute. Channels across the broader solar system. Some of these features that we see extending across other planetary bodies, and they're the biggest types of channels that we see in any other planetary body across the solar system. You have these big outflow channels on Mars that were produced by big mega floods draining ice, what were thought ice fields in the early Paleo Mars, and again some of these are thousands of kilometers long, but their length is not really coming up to the sorts of lengths that we see in submarine channels. So there are other features across other planetary bodies, such as on Titan, for example, and other systems as well. But the channels associated with submarine processes on Earth are probably the biggest in the solar system. So very important features. And of course, as I mentioned in the brief introduction, the deposits from these channels form turbidites that are very common marine deposits that we see in the rock record, and hold lots of clues, if we can unlock them, to the paleo environments that produce them. And many of you, I'm sure, when looking at rocks in the field, will have found turbidite deposits all over different parts and different geologies. So it's a really important feature in terms of understanding how they are laid down. Just see if I can get this to play, just to give you an example of some of the things that we're kind of looking at. So let's see here, if I can move this across. Are you able to see this? Someone could say yes.
Yes.
Yeah, perfect. Thank you. So these are some experiments of a turbidity current with a range of siphon systems and measuring systems. This is done out in Utrecht with Joris Eggenhuizen and a range of other workers, kind of looking at some of the deposit. I'll just replay that, and you can see the complexity, but also the power of these sorts of flows, seafloor hugging currents that are driven by the concentrations of sediment within them, so flowing under their own kind of gravitational forces produced by the sediments that they're carrying. So these sorts of things happen all over and are incredibly important in terms of carrying that sediment load into the deep sea. And of course, these sediments build up over time. The way in which the sediment carried by these turbidity currents and move out across the abyssal plain, build terraces, build channels, and build stratigraphy. And what our team has been doing is trying to understand the nature of these layers and what's controlling the evolution of that stratigraphy as it builds up. What are the processes that are controlling that stratigraphy? And then can we use the understanding that we unlock from these measurements to then go back and look at sedimentary deposits in the rock record with better interpretations of what they may look like. So lots and lots of important things there. And of course, we know that these channels are big and long, but they can also be incredibly deep as well. And that's one of the key features that they have over terrestrial river channels. Terrestrial river channels tend to be, on average, if you took a global average of the big rivers on Earth, you're probably at 5-10 meters. The big submarine channels on Earth are probably are an order of magnitude, maybe a little bit more than that in terms of depth. So typically 50 to 100 meters in depth. And of course, that's related to the way in which the sediment is carried, the way the nature of those flows. And then obviously, as those sediments are laid down, you build up a stratigraphy. And you can see here a snapshot of that, a cross section through one of these channels in a Nummuck channel, and you can see the way in which we can see the overall way in which deposits are being laid down, the patterns, the slopes, both within the channel itself, but then also on the levees, and that tells us lots of information about the way in which this system has evolved over time. And of course, one of the key differences between terrestrial rivers and submarine channels in terms of flow processes is the way in which they are driven in terms of their basic physics. The way in which submarine channels are driven is from the density of the actual water mass as it's flowing, and of course that density has a stratigraphy associated with it, and those stratigraphies, stratifications in the vertical mean that you have tend to have denser fluid with a higher suspended sediment concentration near the bed, and then you have a mixing zone above that where that sediment laden fluid is being mixed with the ambient water that lays above it. And of course the velocity profiles are very different as well, because the flow is being driven by its density, because the shear at the bottom of the flow is entraining sediment as it goes along, so it becomes self-sustaining in certain circumstances. The velocity profiles of turbidity currents are very different to those found in rivers. Typically in river systems, the water flow is fastest near the surface of the flow, at that air-water interface, whereas within density currents or turbidity currents, that inverse is the truth. And we see at the bottom of the flow near the bed, the fastest part of the current tends to be depressed near and towards the bed, and this is what this figure here is showing. So you have a gradient in velocity profile, but you also have a gradient in concentration as well. So you have the denser, faster moving fluid closer to the bed in these turbidity currents, and that turns out to be incredibly important when we're looking at these process to product relationships that I'll move on to talk about. I should also say, just as an aside, of course, what we also find is grain size stratification as well. So stratification in the grain sizes. So again, coarser material being closer and nearer the bed as well. So we see the way in which deposits happen, that you see this fining upward sequences in levees as a result of some of those both stratification and concentration, but also stratification in the vertical of the grain sizes that we see. And we've published a range of work on this, and I'll come to some of the exciting field work at the moment. But Rob Durrell, who's in the team here up at Hull now, has led on a series of papers looking at and trying to model using shallow water equations. And what I'll say, I'll send to the conveners a set of papers in PDF format that I'm citing in the work here, so that you can all read them at your leisure should you wish. So lots of the way in which stratification happens can be modeled as well, and we can understand that by developing models and applying them in slightly different circumstances. And I won't go into the full details of the water model, but it'll give you an idea of how powerful that can be to start to look at some of these features. The model itself assumes a hydrostatic pressure field. And it runs in terms of reducing the problem to a two-dimensional depth average problem. We develop here the model, and I'll demonstrate at the moment for some field work we did in the Black Sea, just to give you an example. But it basically does a source term to create a scalar transport of the salinity. So the density in the Black Sea case is driven by salinity. And I'll talk a little bit about that in a second. We look at vertical structure functions to apply a stratification to the velocity and concentration, and then we can use that to then come and look at the ways in which stratification result in different flow processes in this. So I'll move to the field example. This is some superb fun field work that I did with Jeff Peakle and Steve Darby and Esther Sumner a number of years ago in the Black Sea. Those of you that are aware, the Bosphorus Strait goes through down the middle of Istanbul, or should I say Istanbul's being put where the Bosphorus Strait is, the other way around. But the flow dynamics of the Bosphorus is phenomenal, actually. There's an exchange flow that runs pretty much 24/7, 365 days a year, slightly perturbed by atmospherics at times in terms of pressure patterns, but in the main we have a denser, more saline flow at the base of the Bosphorus Strait, going from the Sea of Marmara into the Black Sea, and then there's a less saline return flow at the surface of the Bosphorus Strait, moving from the Black Sea into the Sea of Marmara. And that density contrast between the Mediterranean, which is more saline, and the Black Sea, which is less saline, as a result of many of the river inflows into the Black Sea, result in this continuous exchange of fluid. And what that fluid has done is it comes out through the Straits of Bosphorus. I'll just use my cursor here, is carve this incredible channel system on the shelf, the southwest shelf of the Black Sea. And you can see this, the flow near the base of the Bosphorus comes down through this channel system over a series of hydraulic jumps in here around this bend, and then bifurcates out into a series of almost deltaic like channels and bifurcations. And what we did is we went out to measure these flows and understand the dynamics of the flow as it moved out the Bosphorus across this plain. And this was done on a series of cruises, first with Turkish colleagues, Izmir, and then more latterly with colleagues in other institutions across Turkey, and a number of them in terms of a piece. We used a Turkish vessel to begin with from Izmir, and then latterly we used the Pelagia, which is the Dutch research ship, and surveyed all around the southwest of the southwest plain of the Black Sea shelf. We did a range of CTD casts, and then you can just see on the back of the vessel here, we also used the National Oceanographic Centre's, so NERC's, autonomous submarine, did a range of bed grabs as well, and his Esther kind of decoupling one of those grabs, having recovered it onto the deck. This was great fun using the submarine. This would go off for 48 hours on pre-programmed missions down near the seafloor. The real great thing about being able to use this submarine was the way in which we could recover velocities down near the seabed. We were using an acoustic Doppler current profiler. That's this blue and red instrument here, downward looking. So that would look down onto the seafloor. And essentially what that is an underwater speed camera. So it measures the velocity of the fluid using Doppler shift, the same way in which you can compute the speed of an ambulance based on the way in which the siren, the sound waves from the siren gets compressed and then extended as it's coming towards or away from you. Uses the same principles here to measure flows. Now these are used lots in river systems to get discharges and flow velocities in rivers, but to measure the currents at the bottom of the Black Sea, if we measured from the surface, we'd get really poor resolution data because these beams go out at an angle, and as you get further and further away towards the seafloor and 100 meters of water depth, they're insonifying huge parts of the seafloor. What the submarine allowed us to do was get much closer to the channels and almost survey this submarine channel in the way in which you would a terrestrial river channel with a boat. So we program the auto sub to skim across the top of the channel and measure the flow velocities in a series of cross sections down through the system. And here you can see it being deployed from the larger Pelagia vessel a few years later. What that enabled us to do is go out and measure these cross sections and measure velocities. So I'm going to show you a series of transects here. So some transects that the autosub went to take out, and then the contours in the back here will also be the salinity as well in a minute, the density. So here are all the CTD casts that we took in the dots on this plot. And you can see we've recovered all of the velocities in different directions. And then look, we've recovered the densities as well, and looked at the density and the stratification of the flow as it's moving down through this channel as well in these cross sections. And what, of course, we were able to do from this is look at the patterns of those flows and look at how the velocity field and the density fields were moving around these channel systems. And we can look at all of these sorts of field data. Excuse me, field data. And then we can also then use Rob Durrell's water flow, shallow water flow model to look at the patterns as well, and then start playing with a series of parameters where we could change the stratification and look at the sorts of patterns that resulted in where the fluid moved to, its shear stress, and where it may or may not then deposit sediment should these flows be sediment laden. We were using the salinity here as a proxy for sediment. And of course, all we're able to do is then compare and contrast the field data here, looking at on the right, to some of the velocity calculated by the model, and then start looking at the differences between the model flow and the data we captured from the field itself. And then we can start looking at what that actually means in terms of model versus the density from the CDT. And then we can start looking at the fit to look at what stratification is needed in the model to achieve the results we see in the field. And that's a really powerful way to start exploring how important stratification of these velocity fields are, stratification of the salinity fields are, in terms of controlling the patterns of fluid flow across this Black Sea shelf. So we're able to do that, and we're able to demonstrate how important stratification is, but ultimately what we're trying to do is understand something about the flow processes themselves as well, in terms of what that might tell us in terms of those deposits. So this is to remind me to talk about perhaps some of the things you'll have come across in textbooks from your days doing GCSEs in geography lessons, where we know that the flow fields around a meander bend essentially spirals, or has a helical flow to that flow as it moves around the bend. And that's because the water, as it goes into a bend, has the kind of outward forcing centripetal acceleration or the centrifugal acceleration essentially that tilts up the flow as it goes round a meander bend. And as a result of the pressure gradient force that's created there, you have a return flow near the bed that results in this kind of helical flow that's outward at the surface and inward at the bed. And that's classical bend flow theory going back to Leonardo da Vinci's kind of drawings. Now, what happens in the Black Sea that we discovered both from the modeling and then also from our field data is the reverse happens in these submarine channels in many situations. And that is because the flow is being driven by the bed, the flow, the greatest outward force of that acceleration force as the flow enters a bend is near the base of the flow. And that means that the fluid at the base of the channel moves outwards and the return flow is near the surface. So the helical flow that goes around a submarine channel bend is inverted compared to a river channel. And that was a major finding, because what that means is there's all of the understanding that we have from terrestrial river channels in terms of point bar deposits, in terms of the deposits that we look at in terms of floodplain sediments of a terrestrial river. In terms of how a submarine channel works, the basic flow processes that are happening within these bends are completely opposite the other way around, due to the way in which stratification works in the vertical. And of course, that also happens in terms of the density. So the outward movement of more dense fluid as the flow moves around the bend also happens. And we see this, what we are calling a decoupling of the velocity core and the density core, which again has been seen in some flows on terrestrial rivers during high concentration flow events. But it was the first time anyone had kind of measured this directly in the field in a submarine channel system. And we were able to start looking at what these flow processes mean for those sedimentary deposits. And you can look at the kind of different types of forces that we were able to kind of calculate the pressure gradients. And we see this movement, as I say, in a little summary diagram here of it working in the opposite direction of what you see in a bend around these submarine channel systems. So that would mean, for example, that we are moving fluid outwards and up onto the levee, and if these were sediment carrying flows, then you could envisage a way in which the patterns of deposition would be very different in terms of the point bar deposits than what you'd see within a river system, where the fines are then recirculated round in the opposite direction. And yeah, this is to remind me to say, of course, that layering up in terms of the fining up sequences that you might see within different types of point bar deposits within a submarine channel system. You may see some of that inversion happening both in the deposits as well as in the flow processes. But of course, there are lots of things that we can then do and go and look at. So we've been doing some more field work. This is from Octavio's work that was done out in University of Illinois, same time I was out there. I wasn't directly involved in this study, but this was looking at flows over mobile beds within the laboratory to look at the way in which the stratification was then looking in training different particles here on the bed and reshaping them, and starting to look at the way in which stratification or different amounts of stratification starts to look at the differences here. And here what we can see is a series of velocity profiles. So this is velocity this is relative depth on the y-axis, velocity over maximum velocity on the x-axis, or sorry, velocity over mean velocity on the x-axis. And what you can see is a very simple model we developed that looked at where the velocity maximums were. So there's a series here. You can see the velocity maximum very close to the bed, and of course a river channel would have so this is the one close to the bed. A river channel would have a normal profile that you just see increasing velocity up towards the surface. But these are just a range of different gravity currents with different amounts of stratification, and that stratification controls, or is controlled by, of course, where the velocity maximum occurs. So more stratified flows with higher velocities down near the bed, and of course that then means different types of forces, different types of positions of the velocity maximum. Means you either get reversal of that secondary flow cell in a bend, or a flow normal like a terrestrial river flow. And that's really important in then controlling where these sediments move to. And Sequeiras's work was able to start looking at some of these processes, looking at supercritical and subcritical flows, and whether or not that was a distinction, where you have supercritical flows entering a submarine channel bend, you'd have this inversion, and subcritical flows where you wouldn't. And we started looking at some of these things. So where the peak density was, the thickness of that bottom layer, we can start to kind of explore these things. But we run into a whole series of problems here, because when I flick back to the plots here, the issue is one of scaling, where we start to think, well, what's the scale of these particles when you think of the scale of the flows that are in the field? These sand grains here, essentially, when you scale up these flow processes, are the size of London buses. So there's a real scale problem in trying to understand the flow dynamics, and trying to have scale similarity where we're looking at these sorts of processes. So there is two ways to go, where we've taken some really valuable results in the flume, such as these here, with a whole host of scaling problems with them, and we take them out into the field or into a numerical an approach to see if we can come past these things, because ultimately trying to scale sediment transport of these types of flows means we're beginning to run into problems with fall velocities of the particles, trying to get the turbulence levels correct for the types of flows that we have, because the turbulence doesn't scale properly either. And then we run into problems with shape functions as well. So it means that we have quite a few problems with the experiments and the scaling that comes well here. And lots of reasons why lots of the lab data maybe tends to underpredict run out of these sorts of currents, i.e. they're very good, the lab experiments are very good with the high fall velocities of modeling collapsing flows that don't go very far. But actually we know from some of the observations that have been made in the fields of not high process data, but we know these currents can run out for very long distances, and that doesn't really make sense with the lab data that we've got, where these flows collapse quite quickly. So the next step as a team was to go, right, well, what do we do? How do we get to these sorts of problems? How can we start to really kind of get to grips on them? And this is where the Congo Canyon work that I want to share with you comes from. It was like, well, can we go to some of the biggest channels that are sediment carrying ones? So don't use a proxy site like we did within the Black Sea. That we got the scaling there by going into the field scale. But of course, the Black Sea is a proxy because it's saline flow rather than sediment laden. A lot easier to do all the kind of oceanographic measurements with saline flows than is sediment laden flows. And the Bosphorus Strait, of course, as I said, is a regular flow. It's continuously flowing, so it makes it really easy to go and work there. Of course, when we go into large submarine channel systems globally, sediments moving around, really hazardous place to put any sorts of instrumentation. And of course, we have the problem of measuring within highly turbid flows, which acoustically is very difficult. The high sediment concentrations tend to absorb all of the acoustic energy in our measurement systems. And if our measurement systems survive the flows, then taking actual measurements within them is incredibly difficult too. but we thought we'd go try. So we've been doing this project for a number of years now, where we went out and first of all used some data that was from a Chevron project. Chevron were looking at putting a pipeline across the Congo Canyon, and wanted to know whether or not they needed to pay billions of dollars to put it to drill it and put it underneath the canyon, or whether or not it was safe to put the pipeline across the canyon. And the measurements that were taken over a year period showed very much that they need to put this pipeline underneath the actual canyon channel system. So the measurements themselves were taken with again an acoustic Doppler current profiler, but it was suspended off the bed of the base of the channel, the green dot in the middle here. So mid water, so about 85 meters off the sea floor, in about I think how deep we were, about I think 1,000 meters down, something like that. And there was a little bit more, sorry, probably between 1,000 and 2,000, something like that. I can't quite recall the depth of the seawater depth, but it was about 85 meters off the sea bed in the middle of the channel. And the beams were down. Remember, the ADCP is an underwater speed camera, and we put it on a mooring line, and then a series of flow events came down through the system over the deployment time, and we were able to take measurements of when these happened and what the sorts of velocity patterns were of these flows moving down through the Congo system. And then we were able to go back with a number of vessels, and this is a map. This is from Ed Pope, who's just moving on from Durham at the moment. So he led on pulling the bathymetric surveys together here, which is again the Congo Canyon mapped in unprecedented detail, and you can see the kind of extent of that survey moving out over waters. And you can see the intricate detail in here of the actual channel at these higher resolutions. We can see the terracing. We can see all sorts of interesting features of the bathymetry. Now this map was used for us to then put in a series of ADCP mooring lines down through the Congo Canyon system. I'll just check. Oops. You can see the image here. So this was, I'll give you the link to John Amos's piece on the work that we did there. But you can see here quite neatly, it's probably a better photo than anything I've got actually, of one of these mooring systems, the bottom looking ADCP here on a mooring line with a series of floats with a big chain as the anchor onto the seafloor, and the silver thing that's kind of hanging there in the middle is an acoustic release, which would allow us to go and recover the ADCP from there by sending a signal down, and that system would then release from the weight and pop up to the surface. Was the plan. I'll come to that in a second. We went in and put a series of moorings all down through the system, 9 of them in total, spanning from up near the head of the canyon system all the way down, way beyond this plot, going right out onto the fan, right out down here, where the channel essentially becomes a real, largely indistinguishable from the plain. So we've got this kind of source from the Congo Canyon and the river all the way out into the deep sea. So we can do the first really source to sink measurements of flows moving from a submarine channel into a submarine fan system. So really exciting novel data sets. All of this went in 2019. And on the 11th, well, it was on the 9th, 10th, and 11th of January, a major failure in here following a high record flood, the one in a 100-year flood event, essentially in the Congo Canyon, in the Congo River, resulted in a triggering a big submarine density current that went all the way down through this system. It basically broke the steel cables on all of our moorings down through the system, and they all popped up to the surface. They all had recovery beacons on them. So we knew that they'd popped up. We knew how quickly they'd popped up onto the surface, because they start broadcasting as soon as they get to the surface. And we knew the approximate timing. The problem was going to pick them up. So this was a bit of a race against time, of course, because back in early 2020 was just as noises began around a strange new disease coming out of Wuhan in China. Rescheduling research trips is difficult at the best of times, but rescheduling ships to go and pick up our moorings is incredibly difficult when a series of lockdown across the globe were beginning to come in. Now, we were incredibly lucky that we had these moorings all floating around in the Atlantic with a treasure chest full of data, because it's the first time a current like this had been ever measured in the field at full scale. But all of the data it was locked on on essentially the SD cards inside the ADCPs, the underwater speed cameras, on the moorings that were bobbing about in the Atlantic off West Africa. And we needed to go and pick them up, and there was no research ship available, etc., etc. And we got called by this ship, who was actually out there fixing the submarine cables, the telecom cables that had been snapped by the passage of these turbidity currents. So unbelievably, they happened to nearly run over one of our. This is needle in the haystack, or needle in a series of haystacks moment. But they actually spotted and recovered one of the moorings, got in touch with us, and at that point we said, well, you're in the area, and there's another 8 of these things floating around. How much would it cost, once you fix these cables, to go and pick up our moorings for us? And it turns out that around £300,000 was the answer. So I was, right at the start of lockdown here in the UK, I was put in charge of essentially remote control of this vessel that is here before you, which is quite exciting to be in remote control of such a large ship. So we were relaying the location of the signals, the EPIRB signals coming from the moorings to the ship, and then planning a course for them to go and pick them up in the most efficient way. And of course, these things are drifting over time, and we only get a location every 12 or every 4 to 12 hours, depending on the settings. We had to be really careful because the batteries were slowly running out on the communication systems, and so there were lots of complexity. But we got pretty much. There's still one we don't yet have back, but we have all of the others back and in our safe possession. And of course, that captured a whole range of interest, lots of BBC kind of interest in this, a long feature article. Lots about the story, of course, of the recovery. And the interesting thing is this underwater avalanche, as Jonathan called it, quite evocative way of thinking about it, is that the way in which it impacted society. So these telecoms cables were severed by these flows. They're 2 of the 3 telecom cables that connect Europe to southern Africa severed by this event, which resulted in a tenfold decline in internet speeds across the whole of southern Africa, right at the heart, right at the heat of the pandemic and lockdowns. So these were big issues at the time, and still are in many ways in terms of our global data security. Lots of these things around submarine cables are incredibly important. However, the data are incredible. And some of the best data I've been involved with in my career. We're only beginning to pick some of the things out of here. We've got a series of research papers on their way coming out, but the real key finding from these data sets are that the way in which these flows operate are fundamentally different to what we've considered, mainly based on our laboratory models. And the key things are, I'll draw your attention to this panel here. So in all of these, I should say, this is time in days along the bottom axis, and then a height above the seafloor in each of the panels on the y-axis, and then the contours are different values of velocity. A velocity fluctuation, which is a bit like a turbulence measurement. We only get a measurement every 10 seconds, so it's not the pure kind of turbulence at high resolution, but it gives you an idea of the pulsing within the flow, I guess. And then we have suspended sediment concentration, which is recovered from the acoustic backscatter. So the way in which the sound is reflected back from the water column can tell you something about how much sediment it's carrying, and we can invert through an acoustic inversion technique, have a really good estimate actually of the sediment concentrations within the flow from this kind of development that Steve Simmons in the team here in Hull has really been pioneering. However, in all of this piece, you can see that the kind of in panel B is the velocity. Peak velocities were up around for this event about 4 or 5 meters a second. But the key thing in all of this plot I want to draw your attention to is this bit here, right at the front of the flow, and this rapidly moving, fast-flowing head is very different from the laboratory models. Normally, what happens in laboratory turbidity currents is that the body of the flow feeds the head of the current. So the body is always pushing the head along, and the head of the current is punching into the ambient fluid, is overcoming the roughness of the seafloor, and the body is constantly kind of pushing the head along and moving it. And that's the model from experiments, thousands of experiments. But these full-scale measurements show us for the first time actually the head races off, like Lewis Hamilton in a Formula One world last few seasons ago, races off into the distance and leaves the rest of the current trailing in its wake. And of course, that means we're getting very different flow processes, very different sediment transport, and as a result, very different depositional patterns as these systems move through. So that's allowed us to recreate a new model for turbidity current and the structure of turbidity currents in the deep sea. And this is a major advance for us. It's looking at how we have this surge model from experiments. Again, here is duration, so along the x-axis, height on the y-axis, and here you can see this top panel. You can see the fast body pushing the head along, having a ballooning of the head up as it billows at the top. The maximum velocity of the current is somewhere back of the actual head of the flow, and of course the stratification and all of the processes I was talking about earlier are governed by this overall global structure to the flow. And we typically have a current head that has that maximum body, a kind of trailing body piece, and the tail. Our new structure based on the Congo Canyon is actually a really short-lived passage of an intense head, or what we're calling a frontal cell, that races off down the canyon system, and then the maximum velocity is compressed within that frontal cell, and then there's a much a longer body and a shorter tail of the flow behind. And of course, the relative velocities are that it's all in here. So what does all that mean? What does it mean for the way in which sediments are laid down? Well, of course, it means that these currents essentially stretch because the front of the head is going so fast compared to the rest of the body of the current. These turbidity currents, rather than being entities that kind of migrate down the systems as a whole, with the head constantly kind of being fed by the body moving forward, and it's a unit of a flow that moves down in the top model here. We have a current here that stretches as it goes off into the deep sea. And of course, as you move down the canyon channel system, with the actual turbidity current, and you're at a point near the top of the canyon, and then a point down near the abyssal plain, what you'd see is a current that lasts for a few hours, perhaps in the upper system. By the time it's stretched and moved down through the rest of the channel, it could last for days and weeks down at the bottom of the abyssal plain. So these currents, in terms of how, in terms of their delivery of sediment, rather than being periodic, punctuated, depositional units into the abyssal plain, what we'll actually see is much more continuous supply of sediment over many days and potentially weeks into the deep sea. That has big implications for the way in which carbon is sequestered from these currents in the deep sea, how those sediments are laid down in terms of the patterns that they produce, and the way in which the stratigraphy is then built is very different from the Congo Canyon results that we've found here. So lots to think about in terms of there. The other really exciting thing, just to finish off on here, is some of the recent work that Ed Pope has again looked at, looking at landslides and triggering of these currents again in the Congo Canyon. And you can see some of what we've got here is a map and a repeat map of the before and after of this big event that came down through the Congo system. You can see the different patterns, but I'll just draw your attention here to this big deposit here that we're interpreting as a landslide deposit in the bottom of the thalweg of the channel here. And if I go to the difference map, you can really neatly see that deposition and erosion. So lots of the channel filled in during this event, and we've got this big deposition in here, and we can see almost a damming of the channel as a result of this deposit. So some real neat linkages between the channel and canyon walls and the flow processes in here, again in details that we've not seen before, and revealing new patterns of deposition driven by landsliding and coupling between the surrounding kind of canyon walls and the channel in ways, again, that we'd not really contemplated or really had data over before. So again, really exciting work, just in the process of going through peer review, looking at, again, some of these dynamic linking. So just to summarize on some of this work that I've talked you through, these submarine channels, they host the longest run-out particle-driven flows on any planet in our solar system. So the huge features. We've shown through our work the stratification of these flows. So the way in which sediment is distributed in the vertical is critical for the way in which they tend to run out for long distances, and ultimately governing the depositional patterns that we see from these systems. However, we can't adequately parameterize that stratification, particularly in terms of our laboratory experiments that have a series of issues of scaling issues in terms of them, and the way in which we then use those small scale particulate gravity current experiments to drive understanding is certainly not there yet in terms of that. So we've gone to the Black Sea, we've gone to the Congo Canyon. We've also done lots of work on Monterey Canyon and in Butte Inlet as well, that I haven't had time to speak about today, to start to look at these processes and this coupling as well. Our results show that there are gravity currents into the deep sea. We've developed new flow models the heads of these currents, the frontal cell runs away from the main body of the currents and results in this flow stretching that extends the duration of flow into the deep sea, and results in long-term flows into the deep sea rather than these periodic punctuated delivery of sediments to the system. We're working now looking at how that changes carbon burial and the efficiency of carbon burial in the deep sea, and the implications of the way in which that depositional history might be changes in terms of how carbon is buried. And of course, then driving that understanding as we move forward in terms of the patterns and the stratigraphy and the coupling of the source to the sink in these systems with this new model will be a focus of work we're conducting going forwards. So with that, I'll unshare my slide deck and say thanks so much for your attention. Hopefully, yeah, kind of giving you all some food for thought, and introduced you to a range of what I think is really exciting and engaging work on some really important problems in terms of the sedimentary geology and the fluid flow dynamics of these incredible features on our planet. So thanks very much, and I'll pass back to I don't yeah, I'll pass back. I'll find the right buttons.
Thank you, Dan. That was very interesting. I remember seeing your work on the news and also in the Geoscientist, and yeah, definitely worth listening to you here now. So yeah, thank you for that.
That's good. Good. And like I said, I will put I'll send the papers on, the PDFs that underpin the talk, and I'll send a few of the links as well for others who might want to follow up some reading.
Yeah, that'd be great. Yeah. Now, let me see if you've got any questions for Dan, please put them in the chat box. I've got one. It might be a stupid question, but here goes.
I always say there's no such thing as a...
Wait till we hear this one. What was, yeah, is there a reason why the submarine channels tend to be, well, are larger than the terrestrial ones? What's the driving force that makes them larger?
Yeah, so there's two fundamental differences. The air, if you think about a river system, the biggest density difference in a terrestrial river system is the interface between the water and the air. So if you think of it as a whole system, you've got this kind of very rapid density interface between the air-water interface. Within a submarine gravity current situation, of course, what you've got is sediment-laden flow, which is denser for sure, but the contrast between the ambient fluid that flow is, that gravity current is being driven through is still water. So the density contrast is nowhere near as much. So you end up with significant mixing between the in certain circumstances, significant mixing between the gravity current and the ambient fluid above. Depends a little bit on how fast the flow is going and the shear forces between the two in terms of how much mixing you get. But the density difference is the key difference between the dynamics of those two systems.
Okay, yeah, that's great. And also, are the submarine canyons all linked to major terrestrial rivers, or you can get them?
Yeah, well, yeah, I think Jeff Peakle, a colleague from Leeds, puts this best. He says that in the whole of geological history, it's probably the worst time to be studying submarine channel systems, because many of them are at high stand like we have now, are decoupled from the river systems that supply them. So you have these big continental shelves that kind of get in the way of making these submarine channel systems much more active. they're almost, many of them are kind of fossil features because they're disconnected from the rivers that supply them, and all of the sediment that the rivers are supplying is being sequestered onto the continental shelf. There are a couple of locations, the Congo Canyon being one, where there's still that direct connection between the river essentially and the very, very short continental shelf between where the canyon feeds up onto where the river comes out. But many other river systems are disconnected from their canyon fan systems. The Amazon's a great example of that. The ones that are most active are the ones that are most coupled. But at low stand, of course, all of these river systems will be coupled very well to their canyon fan systems, and it'd be a much better time to be studying these at low stand.
Okay, thanks for that. I've got a question from Ian. He says, I guess it's hard to match the Reynolds numbers for a model. What unusual fluids and particles would you need?
Yeah, no, great question. Yeah, so one thing that I mentioned as you go through is getting the turbulence right in the experiments is really hard. Just to get the intensities and the scales of the turbulence right. So lots of people have done some really interesting work by using different types of fluid, where we can, for example, index match, so we can actually look at flows in different reference conditions and see through obstacles. So fluid mechanics type experiments which don't have sediment in them, but ones where you can really look at the flow dynamics. Some folks have used in terms of the particles, lightweight particles. So one of the big issues I mentioned as I talked through is the fall velocity is really high, and the scaling is difficult. So one way to get around the scaling is to use low density particles. So they're not as heavy as sands, for example. And by using low density particles, you can get the fall velocities a bit more realistic. You introduce other biases, of course, in terms of that, but yeah, people have used lightweight kind of plastic particles in experiments to try and overcome the fall velocity, which results in the collapsing of these gravity currents in laboratory settings.
Okay. Do you have any more questions for Dan? We've got a couple of thank yous from people.
Yeah, no, I saw those. Thank you.
Yeah. Yeah. It really has been an interesting talk.
Yeah, no, it's great. Thanks. Yeah. If there's other things that come along, then yeah, or anyone kind of is in the shower later on and suddenly thinks of a burning question, then yeah, please do drop me a line. Really keen to kind of let folks know the sort of work we've been doing. As I say, it keeps me out of mischief and keeps me entertained and interested, and it's great when other people are interested too.
Oh yes, definitely. No, thank you very much, Dan. If there are no further questions, I'll just share my screen just to introduce next month's talk before everybody leaves. So not next month, this month, on the 28th of July. So we've got a talk by Clive Edmonds from Stantec. He'll be talking to us about karst engineering geohazard challenges for construction upon the Heath Formation in Kent. It's going to be same time, 7 start, and it's going to be held via Zoom. So it'll be great to see everybody as usual. Hope to see you there. And thank you again for your time and your presence.
Okay. Thanks, everyone. Goodbye.
Thank you all. Bye. Have a good evening.